Quantum mechanics started a revolution that transformed the modern world. It's hard to imagine life without computers, digital cameras, MRIs, GPS, and smartphones. Yet every one of these modern digital devices is largely just a collection of electronic switches that precisely guide and control the movement of electrons through circuits. The first generation of computers used vacuum tubes as switches to guide electrons through a room-sized maze of circuitry. Each tube has a cathode and a plate. When the cathode is heated, it emits electrons that are attracted to the plate. The grid in the center controls the output. If it's negative, the electron flow decreases. If it's positive, the rate increases as the electrons speed toward the plate. Unfortunately, the tube was not very reliable as a switch. The largest computers needed 18,000 tubes, which used a great deal of power and often failed due to overheating. This posed a significant problem.
The big challenge that needed to be surmounted in finally instigating the technological revolution of the modern electronics age is we needed to make circuits smaller. If you have big circuits, then you can't have small devices. So the challenge was, how do we shrink the size of these electronic circuits and really be able to create microscopic versions of them? Well, if you shrink something down into the microscopic domain, the laws of quantum physics become more and more important.
In the middle of the 20th century, physicists knew they needed to replace the large problematic vacuum tube with a more reliable switch that used less energy. To get there, they tested the electronic conductivity properties of solids, such as crystals and metals, at their atomic level. This launched the field of solid-state physics, a huge leap for industry. In the late 1940s, a team of physicists at Bell Labs made a huge discovery. When two gold point contacts were applied to a crystal of germanium, it produced an output signal greater than its input. They called it a transistor, the fundamental building block of all modern electronics. These tiny transistors function as both a switch and an amplifier. Transistors consumed much less power and controlled electron behavior with more precision than their vacuum tube predecessors.
So you need to have the laws of quantum physics at your disposal to understand how to manipulate the motion of electrons and make them go through these tiny, tiny circuits, these tiny wires. And it was the understanding of the quantum domain that allowed people to fashion microscopic versions of circuits, the integrated circuit, where you've got huge numbers of circuits in tiny little areas.
The conversion from large tubes to tiny transistors began the trend toward miniaturization. Now, individual electronic circuits could be soldered together onto one small plate. This led to the early development of the integrated circuit. By 1971, integrated circuits now had over 2,000 transistors on a single chip of silicon, eliminating the need for wired connections. The first commercially available microprocessors were now in production. Using quantum mechanics, the era of integrated electronics was now underway.
Now, the world is your oyster. You can create microscopic versions of circuits that allow you to have tiny laptop computers and cell phones, allow you to have all sorts of devices which, in the earlier era, the electronics would have taken up a whole room, a whole building. Now all of that happens in a tiny little device.
In 1965, physicist Gordon Moore predicted that the number of transistors per chip would double every 12 months, so that the size of the transistors must shrink exponentially as well. Although Moore later revised this miniaturization rate to every 2 years, the microprocessor's rate of progress still far outpaces that of most industries. Today's microprocessors have more than 1 billion transistors. For instance, there are over 2 billion transistors in an iPhone 6. 22 nanometers is the size of the smallest transistors in use today. Once they get much smaller than that, the quantum effects of particle behavior present some unique engineering challenges. Will single-atom transistors inside quantum devices mean the end of Moore's law?
But if we can harness quantum computing, not just using quantum physics to build a device that ultimately does its calculations in a classical framework, but if you can actually do the calculations themselves in a quantum formalism, then the power, your computing power, will grow exponentially compared to anything we have today. And that is hard to imagine where that might take us.
We are approaching the physical limits of Moore's law. Below that is the frontier, the quantum scale where wave-particle duality can be used to our advantage. Researchers are now developing quantum computers that can harness some of the stranger behaviors of particles on the subatomic level. Superposition, the overlapping of particle wave states, and entanglement, where linked particles continue to interact with each other even at great distances. In quantum computing, particles are neither one nor zeros of the traditional binary code. But instead, these qubits, as they're called, can be 1, 0, or both values simultaneously. This means a quantum computer could calculate all possibilities simultaneously, allowing it to process a much greater amount of calculations per second.
People are working very hard today on developing quantum computers, and rudimentary versions do exist. The calculations that are undertaken are not particularly impressive yet, but that is a wonderful step of proof of principle that these ideas really can bear fruit.
Quantum mechanics are not only revolutionizing the data highways, but also the real highways, the ones on which we drive every day. Smart cars will talk to each other, transmit data, navigate and drive autonomously. The quantum mechanical phenomenon of superconductivity, a quantum effect of zero electronic resistance, is behind the super high speed reached by the maglev trains. These coils generate a magnetic field 100,000 times stronger than the Earth's magnetic field and enable both the levitation and the propulsion of the train, making it the fastest train on Earth. Although he disagreed with it, Einstein was one of quantum mechanics' most significant contributors. Einstein had theorized how wavelengths of photons might be amplified in a steady stream, which gave us the laser. Without lasers, there would be no CD, DVD, optical disc technology, no barcode scanners, and no laser surgery. Without laser technology, there would be no fiber optic communication, the light pulse-based network that connects and delivers much of the world's data. Today's fiber optics technology allows for data transmission at about 70% of the speed of light. But researchers are rapidly breaking speed records by designing hollow core fibers to transmit photons through air, not glass. Now imagine a computer that can process this data at the speed of light. Silicon photonics is an emerging technology that eliminates the need for photon-to-electron conversion, which slows the computing process. By keeping this data in its photon state, this technology would allow downloads of large files, such as feature-length HD movies, in 1 to 2 seconds. The next quantum revolution is being born right now. With it will come technologies and tools that break down barriers of space, time, and speed in ways we can't imagine.
You can show from the math of quantum mechanics that were these ideas ever able to be fully harnessed, you could do calculations exponentially more quickly than the device that I have over here. How exciting would that be? I mean, we know that this has already transformed our experience of reality. Now, let this be that little grain of sand in this huge beach of calculational power. Exciting, frightening, thrilling. That's where it could lead.
One of quantum's founding fathers, Niels Bohr, said, "Anyone not shocked by quantum mechanics has not yet understood it." Quantum mechanics, one of the greatest and most accurate mathematical theories ever set forth, redefines what is possible.